Integration techniques. Lesson 1. Reviewing basic integration techniques. The derivative is the instantaneous rate of change of a function. It is the gradient of the curve. The sign of the derivative shows whether a function is increasing, decreasing, or stationary. If the velocity of a moving particle was given by Vt equals 0.05 t take 3 all to the power of 3 plus 2, it is then possible to calculate the rate of change of velocity, known as acceleration. Solution. To work out the rate of change, we're differentiating with respect to t. So dv dt equals 0.15 outside of t take 3 to the power of 2. That's applying the chain rule, where dv dt is also known as acceleration, or at. If you then wish to determine the original equation, primitive function, from the differential equation, dv dt equals 0.15 t to take 3 to the power of 2, you would then need to apply the technique known as anti-differentiation, called integration. Solution. We start with the differential equation dv dt. We then need to separate the variables. So we multiply both sides by dt. We then integrate left-hand side in terms of v and the right-hand side in terms of dt. Note that dv is equal to 1 lot of dv. So our left-hand side will turn into v, and our right-hand side is applying the chain rule of integration. So we add a power to our 2. We divide by that as well. So the power of 2 becomes the power of 3. We also divide by the 3. The 1 here is because the derivative of t is 1, so we're also dividing by that. Simplifying that right-hand side, we get 0.05 outside of t take 3 to the power of 3 plus c. C is a constant and can be any real number. Usually that's defined, or can be defined if we're given some initial conditions. Antiderivatives and primitives. If a function fx equals 4x cubed plus 3x squared exists, then the antiderivative could be written as its primitive function, capital Fx, equals x to the 4 plus x cubed plus c. That is, we integrated 4x cubed by adding the power 1 to the power of 3, which is 4, and dividing by 4. 3x squared, adding 1 to that power of 2 becomes a 3. We also divide by 3. The general solution for a differential equation is denoted by y equals the integral of fx dx. That's your integrand here. And your constant which produces capital Fx, your primitive function, plus c, which is the constant of integration. The power rule for integration is given by the integral of x to the n dx. That is, we're adding 1 to the index, so n becomes n plus 1, and we then divide by that number, which is n plus 1. Add the constant of integration c. The table below summarizes the most common basic integration rules. Here we have a list of many derivative formulas, the equivalent integration formula, and the example. So for instance, if we're integrating a constant, the integral of 4 dx equals 4x plus c. If we're integrating 2 cos x dx, it becomes 2 sin x plus c. There are many more that we can practice during this unit. When you are evaluating indefinite integrals, it is often useful to rewrite the integrand so the calculations are easier to perform. This is common when fractions, radical signs, and fractional indices are involved. When you are asked to integrate, you can also then rewrite them so it's easier to integrate. So for instance, the integral of 3 root x dx can be rewritten as 3x to the half. Makes it a lot easier for us to calculate the integral. The next one is negative 4 over the cube root of x to the 5 dx. Applying our use of index laws, we can rewrite it as the integral of negative 4x to the power of negative 5 thirds dx, which makes it easier for us to apply that power rule of integration. 1 over 7x takes 6 to the 5. Let's just write that as 7x takes 6 to the power of negative 5, and it makes it a lot easier to integrate. Example 1. Solve the following differential equations. So we have dy dx equals 10x to the 4, take 5x squared. Let's separate the variables. Now integrate the left-hand side in terms of y, which is then going to become y, and the right-hand side in terms of x. Here, 10x to the 4, we add 1 to the power. Add 1 to the power, and we're going to divide by it. So 10x to the 4 becomes 10x to the 5 divided by 5, which is 2x to the 5. Negative 5x squared, we add 1 to that power of 2. The index becomes 3. We also divide by that 3. The integral of dy is y. In solving this differential equation here, dy dx equals 4 over root x to the 5. Separating the variables and integrating the left-hand side and the right-hand side. Left-hand side, the integral of dy is going to become y. We add 1 to the negative 5 over 2. You're going to have negative 3 over 2. We also divide by that. Simplifying that, we get negative 8 over 3 lots of root x cubed plus c. Question C, dy dx. Now we have a quotient here, so it's probably best to actually rewrite this by cancelling out like terms. So we rearrange this by separating the variables. Now if we divide x squared into 2x to the 4, we get 2x squared. If we divide x squared into negative 4x, we get negative 4. Let's integrate the left-hand side. That will become y. And the right-hand side, we add 1 to the index and divide by it. Negative 4x becomes negative 4x plus c. Example 2. Now you're going to follow base E type calculations. Here, select the chain rule. We have e to the power of a function 2x. The derivative of 2x is 2, so we must divide by that 2. Now, e to the 2x stays the same. Subtract 2e to the x. The derivative of 1x is 1, hence the integral of negative 2e to the x is negative 2e to the x. Integral of sine 4x. Sine's going to change to negative cos. The derivative of 4x, this composite function here, is 4. So we're going to have to divide by that, which is negative 1/4, because sine turns to negative cos. The composite function stays the same, and we add sc, a constant of integration. 4 sec squared x dx. You then have 4 lots of sec squared x. The integral of sec squared x is 10x. So 4 lots of 10x plus c. Lastly, 2 cos 2x plus 4 dx. So cos becomes sine. So our function is going to stay the same. So the 2x is going to stay the same. The derivative of 2x here is 2. So we're going to divide by that as well. Cos becomes sine. 2x, the angle stays the same. 4 integrates to 4x. We simplify that. We get sine 2x plus 4x plus c. During your study of differentials, you often differentiated composite functions such as y equals 4x plus 9 to the 5, or something like this, to the right. Both of those are examples of the chain rule. In differentiating these, you may have either formally or informally used the chain rule. Consider the solution to the derivative of y equals 4x plus 9 to the 5 to refresh your memory. The formal approach. First of all, let u equal 4x plus 9. Hence, y becomes u to the 5. If we derive in terms of x here, so du dx is 4, and dy du is 5u to the 4. Applying a chain rule of differentiation, we have related rates here. Dy dx is dy du times du dx. Here's your dy, here's your dx. hence it becomes dy dx. Subbing that in, we have 4 lots of 5u to the 4, so 4 5s are 20. U is 4x plus 9 to the power of 4. That's the formal approach. The informal approach is to our 5 here, we multiply our function by 5. The derivative of 4x plus 9 is 4, so we also multiply by 4, and we subtract 1 from the index. Hence, informally, completing that calculation in your head, you would just obtain 20 outside of 4x plus 9 to the 4. So integrating composite functions using an informal approach. How do you integrate these forms of composite functions? The informal approach should be described initially. Steps to follow are: add 1 to the index, so you get n plus 1, as you normally do, and then divide by n plus 1. Derive the function in brackets as a quick mental calculation. Whatever this is, you must now divide the integrand by this. Leave the function inside the brackets unchanged. Observe this approach for 20 outside of 4x plus 9 all to the power of 4, because we know the primitive function is 4x plus 9 to the power of 5. So this, when we differentiate, becomes this, as it was calculated in the first example of this section. So integrate 20 lots of 4x plus 9 to the 4 dx. The power of 4 will become 5. Step 1, divide by 5. The derivative of 4x plus 9 is 4. We must then divide by 4 as well. So rewriting this, the integral is 20 lots of 4x plus 9. The power of 4 has become a 5. Now divided by the 5 and the 4, it cancels out the 20. So we're left with 4x plus 9 to the 5 plus c. That's the informal approach of integrating a composite function. Example 3. Evaluate the following indefinite integrals. So following an informal approach, we're now going to add 1 to this index and divide by it. The derivative of 8x is 8, so we must also divide by that. So we're going to end up with 1 over 32 lots of 8x plus 1 to the 4 plus c. Next one. Our power of 2, or index 2, becomes a 3. We're then going to divide by that 3. First of all, you could also write it as negative 12 lots of the integral of 2n plus 5 to the 2. So we'll add 1 to this index, which is the 3. The derivative of 2n plus 5 is 2, so we divide by that. So negative 12 over 6 is going to become negative 2, outside of 2n plus 5 to the 3 plus c. Integrating composite functions using the formal approach. Like the approach used when applying the chain rule, composite functions can be rewritten and then integrated using a method that involves substitution. This is usually completed by letting a function equal u. Consider this example. Let u equal 3x squared plus 2. Hence, rewriting the integrand, we have negative 30x u to the 4 dx. 2. Let's derive u in terms of x. So du dx equals 6x. Rewrite that by making dx the subject, which is du over 6x. Rewrite the integrand by substituting in dx equals du on 6x. So you end up with negative 30x times u to the 4 du over 6x. Cancel out like terms. So you end up with negative 5u to the 4 du. You can now integrate that integrams in terms of du. So what we've rewritten that integrand is negative 5u to the 4 du. We add 1 to the index and divide by it, so that 4 becomes a 5, and we divide by 5. We cross out the 5s, we end up with negative 1u to the 5 plus c. Rewrite, given that u was 3x squared plus 2, we end up with negative 1 lots of 3x squared plus 2 to the 5 plus c. Example 4. Here we have a composite function. We let u equal 3x plus 4. Du dx equals 3. dx then equals du over 3. Rewrite our integram. So we have our 3x plus 4 becomes u. We replace dx with du over 3. 18 divided by 3 will be 6. And write u to the 4, dividing by u to the 4 as u to the negative 4. We now integrate with respect to u. Adding 1 to our index and dividing by that same number as negative 3. We end up with negative 2 over 3x plus 4 to the 3. So we're replacing u with what we called u, which is 3x plus 4. Rewriting with positive indices, that is the integral of this situation. Example 5. Start by letting u equal 3x take 1. dx equals 3. Rewrite, making dx the subject, which is du over 3. Rewriting our integrand, we get 6 lots of u to the negative 5 and replace dx with du on 3. 6 divided by 3 is 2. Now let's add 1 to our indice, which is negative 4. Well, negative 5 becomes negative 4. Let's divide by that negative 4. 2 over negative 4 is negative 1/2. Replace u with 3x take 1 to the negative 4 plus c. And writing with positive indices, we have our final answer. Reviewing the definite integral. The definite integral is normally referred to as the integral between its limits. The indefinite integral is simply referred to as the integral. The indefinite integral is given by the integral of fx dx. When required, the definite integral appears as, well, you have your terminals a and b, fx dx. The definite integral is evaluated using the first fundamental theory of calculus, written as the following. If you remember your units earlier in your more elementary maths, you find your primitive function and then you evaluate your terminals by subbing in b to your primitive function and subbing in a and subtracting the 2. Definite integral can be found only if the integrand fx exists for all values of x in the interval ab, that is, between values of x that are between a and b inclusive. The algebraic area between the curve, the x-axis, and vertical lines from limits of integration has a positive or negative sign. The general function fx is sometimes positive and sometimes negative. So the integral calculates the signed area, that is the total area above the x-axis here in the positive symbols, minus the total area below the x-axis, which is their negative symbols. So we add up our positives, subtract down areas below the x-axis, and that's the definite integral. The physical area, though, is a positive number. That's when we're adding up our area above the x-axis and the absolute value of the area below the x-axis to give us a physical area. Example 6. Evaluate the definite integral. Step 1, integrate. So we add 1 to our indice and divide by it. We add 1 and divide by it. Next step is to simplify. 2 over 4 becomes 1/2. 6 over 3 becomes 2. We're now going to sub in 2 to a function. Sub in 1 to a function and subtract the 2. The area, or the definite integral, is 6.5.